So in discussing classical computer programming, this fellow at Caltech said, look, in theory there's no difference between theory and practice, but in practice there is. So if that's true for classical computers, it's even more true for quantum computers. So for the next few little slides, I will take you through early state-of-the-art in photonic quantum computing. So here's the idea. We have two two-level systems, which in our case are photons. We have a control photon and a target photon. And we want them to be in a 0 or 1 state. If this was a spin, it would be up or down. In our case, it could be, for example, polarization, horizontal, vertical. And what we want is that if the control photon is in a logical 1 state, we want a pi phase shift between the logical 0 state as shown. And the reason we want that is that ends up entangling the two photons. That is a gate called controlled sign gate, and it's the basis, we'll talk a little bit later, of what you call a universal gate set. If you've got that plus local control, you can do any quantum computation. So let's go back to undergraduate quantum mechanics. I can write the quantum state of this if I've got a photon in both 0 modes, it's 1, 0, 1, 0, it's a photon there, none there, and so on. And if I reflect off of 1/3 mirrors, afterwards the amplitude is reduced by 1/3. There's nothing surprising there, that's classical optics. Okay? However, if the two photons are as shown and meet at that central beam splitter, there's two possibilities now if I work through the quantum mechanics. The two photons can be both transmitted, if they end up one in each output mode. There's two ways that can happen. They can be both transmitted through the beam splitter, that has an amplitude 1 minus eta, where eta is the beam splitter reflectivity, or they can have both been reflected off of the beam splitter, and that has an amplitude of eta. And if the beam splitter is equal to a half, and you can see this in experiments all the time, what happens is when you send in two photons to a 50-50 beam splitter, they bunch. And they either end up both of that output, or they end up both in that output. And that means the two photons never, in the case of it being a half, end up in the output modes. Now this is called non-classical interference. Often in the field it's called Horno-Mandel interference after the people who first discovered it. And if you think about it, it's weird. You're making, well, it's in fact a tiny little Bose-Einstein condensate of two particles. Okay? You can repeat it and make it bigger and bigger. But you're making things that don't normally interact collapse into one state. Now in our case here, the beam splitter is 1/3. And so if you put a third into that, yes, the amplitude is 1/3, but it's negative 1/3. So in other words, when the two photons come in this mode, if they end up in the output mode as shown, they have a pi phase shift as required. And so now, that's my entangling gate. I can take two photons in fibers or free space, send them into polarizing beam splitters, at least conceptually, send them through 3 1/3 beam splitters as shown, and if they end up one photon in each output mode, the two photons become entangled with one another. That's how the first experiment back in 2003 looked. These days you can all but see the steam coming off of it. It's very antiquated looking. It took up about a square metre of space. As I said, even to do, say, factor 15, you would need 4,300 gates, and to do an interesting quantum computation, you need tens of thousands. And so if that's the scale that you're stuck with, this will be the eventual photonic quantum computer. That's probably not going to fly, so we need to miniaturize. There's been a lot of work done around the world. Jeremy O'Brien's group in Bristol, in the UK, and also the Quarry University here in Australia, at making waveguides written into glass, where now the distance between the waveguides can affect both the reflectivity of a beam splitter and the phase. And you can write entire circuits into glass, and this is being done, and the chips end up being, as I said recently, the size of your pinky nail. I'm going to skip. Oh no, okay, I guess we're going to talk about this briefly. The interferometer approach, the problem, you would never build that. A different approach is you can just send the control and target photons into a partially polarizing beam splitter, which you've made so that it's, say, 1/3 reflective for the horizontal component, perfectly reflective for the vertical. That then gives you that central interference, a couple more beam splitters gives you outside ones, and that becomes a compact little gate for doing entanglement. It lets you build a 2-photon cluster. If you want to build a 3-photon cluster, you add one more polarizer and one more photon. Building the gates is not enough. You need to measure what's going on. So I'm going to go back to the idea of measurement, at this point, the output measurement. If you did a second-year optics course, you might have done measuring the polarization of light and come across something called the Stokes parameters. It's basically how much horizontal vertical, how much diagonal anti-diagonal, and how much right-left polarization is there in the light beam. And then, once you know that, you can plot a position on the Poincare sphere. This, in fact, is older than the Bloch sphere. And you can come up with a coherency matrix. Again, this is older than quantum mechanics, where the population, the diagonal is the population and the off-diagonal is the coherences. So, for example, if I have a Stokes parameter S1 equals to 1, then I have horizontal polarized light, there's no vertical, there's no coherence. There you go, there's horizontal, diagonal, right circular. And I can even represent this unpolarized light. I've got equal probability of seeing horizontal vertical, but there's no coherence. Well, that just anticipated quantum mechanics. Old slides, it's meant to be an arrow. Coherency matrices turn into density matrices. And so in quantum systems, what I want to measure is the amount of 0 and 1, bottom level, top level, ground level, first excited level, whatever the system is, and then the coherences between them. And if I just measure the parameters as shown, I can recreate a single qubit state. For 2 qubit states, I need to take, at a minimum, all the pairwise combinations. So if you don't like horizontal and vertical because you're from a condensed math background, just think of that as 0, 0, 0, 1, 0, 0 plus 1, and so on. And if I do that optically, I get out fringes. So for example, if I have a pair of photons and I fix one analyzer at horizontal, and I turn the other one from horizontal through vertical back again, I might get a fringe that looks like this. And what that tells me is that I look like I have a pair of horizontal photons, and I don't have one horizontal and one vertical, so I get no results when I want both. It's a so-called coincidence fringe. These measurements are just points on that fringe. And after I've done that fringe, I can start pulling out information about the system. In this case, I know that I have a pair of horizontal photons. But I could do a different measurement, where I could fix the first polarizer at 45 degrees. And I get a different set of measurements. Sorry. So if I have a pair of horizontal photons, that's the coherency matrix I get. If I have a pair of diagonal photons, this is the coherency matrix I get, which is a total field full of ones. And it's one or the other. But if I have an entangled pair of photons, I get both curves. So it looks like I've got a pair of horizontal and a pair of what? What's going on? And in fact, I get an impossible set of correlations. It turns out, and this is not just for photons, it's for any pair of entangled quantum particles. I get correlations that look like I've either made a mistake or I'm cheating. Okay? So I get correlations that make it look like I've got either a pair of horizontal or a pair of vertical photons, or a pair of diagonals or a pair of anti-diagonals, or a pair of right and a pair of left. And when I get a set of correlations like that, that tells me I have entanglement. The coherency matrix for that looks really weird. For example, this says I've got equal probability of pairing a pair of horizontals with a pair of verticals, and a strong coherence between those probabilities. And I'll never see an HV or a VH. You'll notice that for 2 qubits, I need 16 measurements. For n qubits, I need 4 to the n measurements. And you can start seeing the exponential power of quantum mechanics when you're storing information in quantum systems. You get this exponential blowout in the number of measurements you need to fully understand what's going on. skip this slide. These are just some curves that we take in the lab. You can define on this Poincare sphere a degree of polarization. If you're on the surface of the sphere, you're fully polarized. You have a vector that goes from the middle of the sphere to the surface. If you're in the middle of the sphere, you're completely unpolarized. That's for classical light. For quantum system, that's the coherence. And here are some numbers we took on a system of analyzers we did here. So the discrimination is the Stokes parameter divided by the degree of polarization, in other words, how coherent you are. And here are some numbers we took with very coherent measurements of diagonal, anti-diagonal, horizontal, vertical, right, left. The only unusual thing about those measurements is the system we used. We did use wave plates and detectors, but the wave plates and detectors were in the eyeballs of this animal. This is something called a Gonadactylus smithii. It's a mantis shrimp off the Barrier Reef. Its name means genital fingers, and it's a stomatopod, it's a stomach foot. And in each eyeball, it has the ability to measure, it turns out, horizontal, vertical, diagonally, anti-diagonal, and in these two rows down here, right, left, circular, polarized light. And it actually measures the Stokes parameters and gets optimal polarization vision. Okay? Now the reason the animal does that is, well, there's an advantage if you can get all the polarization information when you're in a partially polarized background. But it's the idea of optimality. So, okay, nature's got there ahead of us, but for quantum systems, we're going to have to do these optimal measurements as well. They're also delicious. It's good as a physicist, you don't often get to eat your experiments afterwards. Okay. It's not enough to measure state measurements, you also need to measure processes. So, as a physicist, you're really worried, I take some system, I send it through this black box, what did the black box do to my system? Well, it turns out you can figure that out as well. Here we show a Poincare sphere again, but if you want, just think of it as a block sphere where that's up. The identity process does nothing. Sigma x rotation rotates me through the right circular, z through the diagonal, and then y back to horizontal as shown. And if I want to know what a 2-qubit process does, I need to do pairwise measurement of those block processes, I, x, y, z. And there I get a horrendous exponential blowout, 2 to the 4n measurements. And you can see, again, this exponential power that's in computing systems. If all you had to do, if all you had was the ability to encode information in quantum systems and then do these measurements, there would be no quantum advantage. Because you're getting this exponential blowout of the number of measurements you need to figure out what's going on. So where quantum computers are clever is they let you do this encoding and they remove the need to do this full tomography to understand what's going on. When you get process measurements, you can, a density matrix you can think of as a table of state measurement outcomes and the coherences between them. Is it horizontal, is it vertical? You can do the same thing with the process. You can think of this, for example, this controlled sine gate I talked about earlier is do identity to the control or not the target, or coherently do identity to the control, that is do nothing, and do a Z flip to the target, all the way through to do Z flips to control and target, but with a negative coherence compared to everything else. So this is kind of the space of possible processes, and you can do a table then where the diagonal is the populations, II, IZ, ZI, ZZ, and the off diagonal are all the coherences. The one on the left is ideal, the one on the right, this really is typical data these days. This is what it looks like when you measure it in the lab. And you can go through and put a number on it, and at first it looks like we horrendously don't know what we're doing. Back in the early noughties, we got things working 94% of the time. With hard work, we dropped it 5%, but we also upped the accuracy. So we're now good to 1 part in 1,000, and we've got those numbers back up to around about 98% now. If one gate works 90 to 95% of the time, then 2 gates should work no more than 90%, 80 to 90% of the time. Let's just keep that in mind. I might just skip this. Yeah, skip that. Okay. Before I get onto applications, let me just briefly talk about the road ahead for photonic quantum computing. Keep in mind, I started the last lecture by saying there's a ton of different systems. There really is. Superconducting circuits. This year, people have got nanomechanical resonators quantized. So they're seeing entanglement between that and an external field. Okay, so there's a ton of different systems, but all of them have their own problems. In photonics, we're going to need these cluster states that I described earlier. And the building blocks we've got are these heralded gates, where we bring in 2 photons and detect them, and another 2 to do the actual work. And that requires 4 input photons, 2 perfect detectors, and 1 gate. Okay? And then if I wanted to make a 3-qubit cluster, that requires 7 photon sources and 4 detectors. And you can see how the scaling goes. And the problem is, earlier I said that this spontaneous downconversion process is what we use, but it's spontaneous. What that means is, if I send in a pulse now, it's not guaranteed to make a pair of photons now. It's only got a probability of making a pair of photons, 1 part in a million. So if I want 4 photons, I need 2 pulses to occur. That only happens less often. Typically in the lab, we can get that to happen once a second. Now if I need 7 photons, and I'm doing it with pairs, I need 8 photons. Well, that only happens once every 4 hours. This is not a way forward to build a decent machine needing thousands of photons. So we're going to have to walk away from this process. And the other problem with this process is, say I've made a pair of photons and I've detected one, and I think I've got 1 and only 1 photon. I've got a small probability of there being 2 photons. That small probability increases as I up the input power, and everything that I like about my gate gets worse as I up the power. So these green, blue and red curves are various measures. I guess the most important one is the red, the amount of entanglement. I'd like that to be 100%, and it very quickly drops to 70% as I up the power. So we need a better photon source. I'm going to skip what we did in the lab to do it. There's 2 different ways people are looking at this. This is from Franco Warren's group at MIT, who we work with. They're going to take a whole lot of downconverters on a chip, run them all, and on every one of them ask, did you downconvert? Did you downconvert? Did you downconvert? And if the answer is yes, say on this third one is yes, it'll get switched through to the output. This fixes the problem of how often can you get the photon. So now you can get a photon every shot if you get this working high enough. We need better detectors. We're working with NAM at NIST, and in fact in the lab tour you'll see we have a fridge which sitting at the bottom we have a cryogenic bolometer. This is a nice idea. This is some superconducting absorber weakly coupled to a thermal sink. And when a single photon comes in, it disrupts the superconductivity. You go from superconducting to normal conducting state, and you get a big pulse in transimpedance pulse, and that tells you that a single photon came in. In fact, this is a picture of the device we've got downstairs. It's this central pad is the detector. The efficiency with the anti-reflection coating on the detectors downstairs, we hope, is going to be on the order of 98.5% to 99.5%. So we're getting there. We're getting there. What about better single photon sources? Dick Baumeister's group at UCSB, who we've also been working with, have been working on quantum dots. This is a really beautiful, highly engineered system where they've now got, this is a quantum dot in a cavity, and the coupling between the dot and the external world is now up to 96% coupling. It's truly one single photon because of the way the quantum mechanics of the dot works. They understand very well how to strain the dot so that they can make it non-degenerate, and they're starting to produce pairs of entangled photons from these dots. And pairs of entangled photons is the raw value for a cluster set. Let's skip that. So the idea is, this is the kind of thing that the photonic community is working towards, is you'll have some source of single and entangled photon sources, some switching yard, some set of gates that will all be on a chip, and some quantum memories. And you'll hear a lot more about possible things for quantum memories, I guess starting tomorrow with Andre Luton's talks. And then some output detectors. All right. I had a question earlier about, I made some comment at the beginning to talk about simulating quantum systems. Okay, so Richard Feynman, in a really good paper back in 1982, I actually do recommend this paper for those of you who are sitting up the back surfing. Go download it now, you've got access to the library. International Journal of Theoretical Physics, Simulating Physics with Computers. And he said we know how to simulate quantum systems. We've got Schrödinger's equation. We know very well how to use it. But the problem is, every time you add another particle to Schrödinger's equation, you double the size of the computation required. It blows up exponentially with the number of particles. And so really, simulating quantum mechanics on a classical computer is hopeless. Now, this was a fairly deep insight for 82, and the follow-up insight was, well, maybe we'll be better off using quantum systems as a computational building block. It was a very nicely thought out thing. If you go look at the diagrams from the paper, I quite like it. It's all photons and calcite beam displacers, which is the kind of thing we use today. It was well ahead of its time, and no one did anything with it. Feynman then ended up dying in 88, and no one did anything with it until 96, when a physicist from MIT, Seth Lloyd, said, yes, look, Feynman was right. You can take some initial set, by now we were using the language of qubits, of quantum particles, qubits, send them through a series of gates, and at the output, get an arbitrarily accurate approximation to a quantum problem. So the paper was called Universal Quantum Simulators. And it showed that Feynman was correct for a very large class of quantum systems. In fact, there is now a significant vocal, and they may even be correct, minority of theoretical physicists who really turned this around and said if you cannot do this with a quantum system, it's not physical. So they've made this their test of physicality, and they're starting to apply that particularly in the areas of condensed matter where there's a lot of options you could have. And they're asking, can we simulate it with this approach? If we can't, it's not a physical system. Okay, so from the point of view of an experimentalist, that's great, but that doesn't actually give you a recipe for learning something about a physical property. So then at Harvard, Alan Skorogutsik in 2005 said, yes, look, here is a recipe for using that approach to calculate the energy of molecules in quantum chemistry. And it's a so-called eigenvalue problem, so it changes Schrödinger's equation into a phase estimation problem. And I'll show you a little bit what I mean by that. And you can also simulate chemical reactions this way and a bunch of other things. So I talked earlier about the quantum chemistry. So here's quantum chemistry 101. It's basically an electronic structure problem. There's the Hamiltonian you need to solve, and you want to find the energy as a function of the nuclear coordinates, and you get these kind of potential energy surfaces that end up as the solution. And as I said earlier, once you have that surface, you have nearly all of modern physical chemistry. So computational chemistry says, okay, we'll take that system, we'll represent it on a classical computer. We have an exact algorithm, the full configuration interaction algorithm, but it blows up exponentially. Because it blows up exponentially, we're going to fix it using approximations. And there's this tree of approximations taken from a paper by Jim Anderson. The quantum simulation says, well, we'll take the wave function that we're wanting to do, something like chemistry, and the Hamiltonian associated with that, and we'll map it onto a different system. In our case, it was an optical system. And then we'll emulate that system and get the answer out. So if you look at where quantum mechanics is giving you a computational advantage, I talked about factoring. For those of you who read these things, there's the advantage. It's terrible. The configuration advantage for quantum chemistry is huge. You go from exponential blowout to a fifth order polynomial. To a computer scientist, that means you're done. Fifth order polynomial is easy. To an experimentalist, it's like, really? Fifth order? Chemical dynamics, second order polynomial, that looks better. Molecular properties, this is quite nice. If you want to know something about, for example, the dipole moment of a given molecule. Normally, you'd need something like D calculations to do it. With a quantum computer, you can do it with a single calculation, no matter how complicated the molecule. That's really very nice. Single query. And protein folding. That's the biggie. That's kind of the great white whale of quantum chemistry. There was a paper on the archive last week suggesting that you cannot understand properly the coiling of DNA without understanding the fact that it's an entangled bound ground state. Well, I mean, the ground state of hydrogen is entangled, so that's not a deep revelation on its own, but they had some suggestions on how you would start solving that problem. Well, let's have a look at hydrogen. Simplest molecule in the universe, 2 atoms, and we're going to make it even simpler. We're going to let them have 1 electron each. We're going to form molecular orbitals. There's the ground and excited state. And there's 6 basis states due to Pauli's exclusion principle, as shown. You can't have both up or both down on the same level. You can take that Hamiltonian, and it's a 6 by 6 operator, and it has this 2 by 2 block structure shown in blue, black, and red. That was extremely familiar physics even to Dirac. I really like this photo. So there's Dirac soldering for molecular hydrogen. So this is very well known. What Dirac wouldn't have known is this, that you take that Hamiltonian, you map it onto unitary evolution onto another system, let that system evolve, do the measurement at the end, and out pops the answer. Here's the system we built. There's a single control qubit. It can be 0 or 1, or any superposition. Actually, you send it in 0 and it goes through a gate called the Hadamard, which turns it into a superposition of 0 plus 1. And then you send it through an entangling gate onto a register that's encoded with a lot of qubits. And then at the output, you throw all that information away and you read out a single bit, 0 or 1. Okay, now that doesn't look like that should be useful, but what that lets you do is read out 1 bit at a time, the phase that you're estimating, which you can map back onto the energy. It scales polynomially, not exponentially. Hydrogen's the simplest thing you can do, and you need to do this tricky, controlled unitary that's operating on many qubits. Well, in the case of hydrogen, we're down to a single control qubit and a register of 1 qubits, so it's a 2 qubit gate. We know how to do that. How am I going for time?
10 minutes.
10 minutes. Okay. So we use a technique called shortcuts through higher dimensions. And there's, how many people here read Hitchhiker's Guide to the Galaxy? Please, someone put a hand up. Okay, great. So you know it starts with big, space is mind-bogglingly big. You think it's a long way to the shop for a pack of peanuts. It's nothing to space. Space is tiny compared to Hilbert space. Hilbert space is huge. Right? Because every time you add a particle, you get an exponential blowout in the size of the space. We're going to use that now. Say you wanted to build a 3 qubit gate. The Toffoli, I talked about it earlier, is the basis of all reversible classical computing. But you have only 2 qubit interactions. And this is often what happens in nature. If I bring 2 spins up, they're going to interact strongly with one another, but they'll tend to shield one another from spins further on. So 2 body interactions are kind of the default. Well, I can expand that gate out into a bunch of 2 qubit gates. This black dot means that's a control operating on a target down the bottom. Okay, so I can do 6 of those black gates, they're control not gates. If I wanted to do a 4 qubit Toffoli, then I need on the order of n squared of those gates, and it blows out. You can get around that by using ancilla qubits, and then you need less gates, but you need 12 times the number of qubits in the problem. And this technique I'm about to show you, where you skip into a higher dimensional space, lets you compact things down, and really the trick is as follows. Here are my 2 controls, C2 and C1. I bring my target in and I split it so that some of the information is isolated from everything else that's going on when I come back. And when I do that, what I do is I take my information from being in a qubit, a 2-level quantum system, and I put it into a 3 or 4-level quantum system and just operate on the bottom levels. So that's where I'm using the higher dimensions of Hilbert space. It's easy to write down the maths. It's hard to do, except in optics it's kind of easy because you're using polarizing beam stir. It's a powerful technique. Say you wanted to use a triple control Toffoli. Now, why would you want to do these gates? It turns out when you're trying to do something like Shor's algorithm or the more interesting quantum simulations, you need these more complicated gates. So if you had a compact way of doing that, that would be good. You could do it like this, but that would be that would require something like 16 gates normally, but you can collapse that down to 5 with this technique. You just nested the problem twice. Similarly for a double controlled unitary, blah, blah, blah. We need a controlled unitary for the quantum simulation, so we end up using this trick to do it. And in the lab, it looks like this. So we use, I said earlier, we have these partial polarizing beam splitters where photons come in and they interact in strange ways, and that's what we use. I'll skip the Toffoli. And how well did the gate work? Well, we did a controlled rotation around the z-axis by an angle theta. If the angle is pi and 4, in the literature that's called the T-gate, this is the real and imaginary parts of the process. That's very close to ideal. If it's pi and 2, it's called a J-gate. If it's 3 pi and 4, it had no name, so we named it an L-gate after the first author. He's still cranky, I say to that. And if it's theta equals pi, it's called a Z rotation. And the numbers are the important thing here. This works between 94 and 98% of the time. So we get these gates working very well. So we take one of these gates and use it in quantum chemistry. So the problem we were trying to do is molecular hydrogen. We take the pair of photons we've made, send it through one of these gates. The green curve here is the MATLAB calculation for the full configuration interaction calculation on the ground state of molecular hydrogen to 50 bits of accuracy. The blue data points are the results of the quantum computer we built in the lab, and they agree to 6 parts in a million, also known as close enough for government work. Okay. In fact, we did the ground and first 3 excited states. Each of those dots is a calculation from the quantum computer. They're all correct to 20 bits. In fact, we ran them up to 47 bits just to see if we could, and we could. Okay, you said 2 gates earlier only work 80 to 90% of the time. How come this didn't give us a wrong answer? Well, it did, but we used a simple majority vote technique. So we were reading out the expansion. So say at the 10th bit, we got 29 or 28 zeros and 2 ones, but we took a majority vote and said, well, that's probably overall a 0, not a 1. And we did that for each of these data points. I'm going to skip this. We did lots of work on asking what happens when the algorithm goes wrong, and it turns out you can recover quite nicely. Okay, so what next? Well, you know, molecular hydrogen, 2-qubit problem. I have a colleague at Perimeter in Canada who said, look, any experiment with less than 10 qubits is cute but useless. Really nice to have a year of your life dismissed by a theory colleague. But I agree with you. It's kind of like a baby with an abacus, right? It's like, oh, isn't that nice? But you wouldn't ever use it in anger. So why are we hopeful? Well, we're hopeful because there's problems our chemistry colleagues have identified. It turns out benzene you can barely do with full configuration interaction. Caffeine, which is my favourite legal molecule, you can't, or you barely can. And cholesterol you just can't handle at all. And yet, if you had just a handful of qubits, a few hundred qubits, as opposed to thousands and tens of thousands, you need Shor's algorithm, suddenly you can do full quantum calculations, including configurations in space, etc. in this chemistry. Oh, right, yes, this is a famous Sid Harris cartoon. So, complicated maths, then a miracle occurs, complicated maths. I think you should be more explicit here in step 2. By the way, how many people here mark undergraduate physics tutorials and things? Hands up if you do. Okay. How many people have seen this approach used? Yeah, right. So, I've just kind of done that with quantum chemistry. I've said, oh yes, we've done 2 and we're working towards 600, but now I want to show you where the miracle is. We need to do every part of the algorithm in a scalable way. So this input itself needs to be calculated with a quantum computer. And the way you do it is this. Say you had a Hamiltonian of 3 quantum systems, 1, 2, 2, 3, and 1, 3. The total Hamiltonian is just the sub two-body interactions, and that's fine, that scales brilliantly. But what you can't do is take a unitary evolution that's just the unitary evolution of 1, 2, 2, 3, and 1, 3. That doesn't work. The solution is you take these Hamiltonians and you slice and dice into very small unitary evolutions, and you repeat, you repeat, you repeat. And the finer you slice and dice them, the better the approximation. So in terms of telling us what we need to build in the lab, we're going to need more gates than 2. We now very well have mapped all of chemistry, excitation operators, number, double excitation, into gate sets. So we know the gates that we need to build. And we know we have trade-offs now for errors. So it turns out the error I said before of about 6 parts in a million, energy in quantum chemistry is measured in a unit called Hartree, because obviously joules is too complicated for chemists. But this kind of black line here is known as chemical precision. That's where most quantum chemists are happy. And we know now how to scale those things. So I'm going to leave that there. On Friday I'll come back, and I've said that entanglement makes quantum computing powerful, and now on Friday I'll show you how you can do quantum computing without entanglement. So with that teaser, thank you for your attention. Thank you.
Do we have questions? Yes, please.
It has to do with detectors, because you mentioned your superconducting detector. Is this sort of like a fundamental limitation of quantum computers, that they have to be cold?
It's a good question. Do quantum computers have to be cold? At the moment they have to be, because our technology is crude. So there's no, in principle, reason you couldn't have an efficient room temperature, for example, photon detector. And in fact, the reason that makes me say that is if you look at something like photosynthesis, it's a warm, wet system that is very, very good at taking single quanta and efficiently turning it into energy. But our level of engineering ability compared to natural systems is still quite bad. The other interesting thing about photosynthesis is earlier this year there was a couple of papers in Nature and Science suggesting that the reason that plants, that the molecules work so very well at that is they're actually exploiting these features of coherence and entanglement in a way that again is not showing up in the normal chemical calculations, where you approximate away all the interesting behaviours so you can do the calculation. But if you do the normal calculations of photosynthesis, it shouldn't work as fast as it does. So how photosynthesis works is you have a donor ring of molecules, and they're in some delocalized state. Inside you have an acceptor ring of molecules, and then there's some center that turns it into an electron, which pops out and gives you energy to the cell. The photon comes into the donor, and that energy is very quickly moved into the acceptor ring, about 4 to 5 orders of magnitude more quickly than the best current chemical calculations, unless you take into account the coherence and the entanglement. So, is it an in principle? No, but it's an in practice limitation. At the moment, we do need cold things. The superconducting systems are cold. The ions can be room temperature, but they work better when they're cold. The cold atom systems are by nature cold. So
there's another question that follows on from roughly what we were talking about. So you mentioned DNA and proteins and all those sort of things, and how they have they quickly find the state of structure in which they perform their function. So do you think that the bad explanation in traditional chemical sense is due to some sort of quantum correlation?
The real answer is we don't know. We suspect there are some systems where this quantum behaviour is very important. There's been suggestion by Indian theorists, for example, that that there are quantum behaviours and that there's a version of Grover's search algorithm going on when you look at protein behaviour. We don't know. My guess is, though, that we will probably find some biological systems where there's clear quantum effects being exploited, because if it gives them an advantage, particularly if it's an exponential advantage, there's a really strong evolutionary driver to do it. They'll be warm and wet, and once we've found them, we will try and reverse engineer them as quickly as possible. It's kind of like a bigger problem in, say, modern chemical synthesis. There's a lot of things that we can currently make in high temperature, very toxic reactions that natural systems do, again, in room temperature, wet systems without difficulty. Right? And we know there that there is a solution, we just haven't yet reverse engineered it. But we're there with quantum systems as well.
Are there more questions? If not, let us thank our speaker for